Hi everyone, we're going to look at alkenes today. So this will feel a bit like the haloalkanes topic we did. We're going to look at naming them, their structures and some mechanisms as well. So you're going to need the alkenes booklet, the orange one. And we're going to start by looking at isomers. So there's a new type of isomerism going on here. So on your first page here, you've got a little summary of the types of isomers we've met before. And the new ones we're going to be meeting. So we're going to meet the geometric ones in this topic, and we will actually meet those this year. That's been updated since this was made. So I've brought with me a few models to help me out. You won't necessarily have one, but I'd be interested to know if you've got anything at home that you can substitute for this kind of thing. Okay, so this will help us to look at how these work. So first thing I'm going to look at, this is a butene, a form of butene. You might be able to tell me which type. You could pause it and tell me there. It's but-1-ene, but-1-ene with the bond at that end. And if I wanted to make isomers of it, well, I can make a chain isomer by breaking bits off and just swapping them around. So I've got the same molecular formula, the same number of atoms, but a different structure. That's a chain isomer. I won't do the position isomer because it would take too long, but I could have that double bond there for the position isomer. We'll be doing that later. And the functional group isomer, possibly the harder one to remember. Is that I just stick it around to make cyclobutane. So those are the types of isomers we've already met. Okay, if I wanted to draw it, there is a new way that we can draw these. You may have seen me earlier on in the year sort of hesitating about how best to draw these at that point because we hadn't yet met this idea, but that is the shape around a carbon-carbon double bond. Okay, so I would draw butane, so but-1-ene, like this. Okay, I would personally I'd draw it with those angles shown. Now, when you're drawing a mechanism later on in this topic, you don't need to do that, but that's going to help us for this topic. So, the type of isomer we're going to be talking about today, the geometric isomers, appear if we've got different things around the double bond, a specific set of different things. So you'll remember from making these in the past that these carbon-carbon single bonds, things can rotate. So if we take this carbon, I've currently got a hydrogen at the top and a methyl group at the bottom, I can very easily twist it round and swap those two over. The advantage of making this is that I now see I can't do that with a carbon-carbon double bond. You might be able to see that attempting to twist. I cannot swap, say, this hydrogen and this carbon about. Can't do that. And I can't do that. Okay? So that is the first thing to notice about the double bond. So that means that this atom bonded up here might be different if it were bonded down there. So let's find out. Let's find out if I can make an isomer of but-1-ene by swapping the two things here. So that's the drawing of but-1-ene that I've done. If I swap this hydrogen for this from the bottom, have I changed my drawing? I can go there now. Well, no, I haven't changed my drawing at all, so I haven't made an isomer there. I haven't changed it. So maybe if I swap these two, so that instead of having the carbon at the top, I've got the carbon at the bottom and the hydrogen in the other point, at the, well, vice versa. Well, now I've got that, looks slightly different, but as you're familiar with, no matter which, it doesn't match it yet, but I can just twist this round and I still get back to that. So the way we phrase this is but1ene does not have geometric isomers, and the reason is it doesn't have two different groups on one individual carbon. So the way to think about that is I need to work out if I've got geometric isomers. First of all, I need to just look at each carbon in the double bond independently. One of my carbons has got two distinct groups attached to it. That's a clue that it might have geometric isomers. Does my other carbon have two distinct groups attached to it? No, it doesn't. So therefore I can't have geometric isomers because this carbon at the end has meant I can't do that. Okay? So, you might be able to see where this is going. Let's start to investigate another isomer of butene. We're going to do but2ene. Right, so but2ene, my double bond there this time. Let's do the same process. Now, one trap is it looks very symmetrical. It looks like I've got lots of the same group, so you might think I'm not going to get geometric isomers. But let's do the same thing. I'll cover one side. That's one carbon in the double bond. Does it have two distinct groups attached to it? Yes. And the other one, does it have two distinct groups? Yes, it does. Again. So, both the two carbons on either side of the double bond each have a different set of atoms on them, so we should be able to get geometric isomers for this. And the way we name them is using some letters. Let's just double check that there wasn't anything else I wanted to talk to you about first. No, okay. So we use our UPAC convention is to use these initials from German words. This would be called Z-butene. And it'd be called Z because of a word I can't pronounce, zusammen or something, together. Okay? In this one are two methyl groups, which are the more interesting group. We'll come up to that more in a minute. The more interesting thing, the thing that isn't hydrogen, is a methyl group, and both the methyl groups are at the bottom of my model as I hold it, or at the top as I hold it, but they're both pointing in the same direction, they're together. The opposite would be entgegen, or E. Oops. So, here's my new one. I'll get rid of that old one there. So, that's but2ene. It needs something to finish its name. It's Z-butene. With a hyphen. That's a Z, not two. Z-butene. They're together. And the way I might check that is you want to draw a line. You want to imagine a line going across your double bond like this. And you look for the highest priority groups, the most interesting groups. And if they're on the same side of that red line, that is the Z isomer. Can we convert it to the E isomer? No, we can't because I can't rotate it. I'm going to need to break some bonds and have a different arrangement in space. There we are. Okay. So that is E-but2ene. Okay, E-but2ene. Can I match it up to that? Yes, I can. There we are. Oops. Well, you get the idea. That is a drawing of that molecule. And that's the E isomer. Okay, ways of remembering those. We used to use the words cis and trans. We're not going to worry too much about that right now. But trans is our sort of opposites, so that is trans. Don't know too much about that one. The little mnemonic I like to remember for the Z is that with Z they're on the same side. Z is on the same side, so Z for two things pointing, the two highest priority pointing in the same direction. Okay? How are we doing for time? I might have to stop this video, I don't know. Oh, we'll be okay. Okay, so that's those ones. It gets a bit more complicated if we have a more complicated alkene. So, with these two, it was easy to decide on the priorities, on making the methyl groups the highest priority. In a more complicated case, like this one, we still need to be able to decide on the highest priority groups. Okay? So, luckily we've got a set of rules. They're in your orange booklet as well. And it's slightly more complicated. Now might be a good time to pause the video and have a go at the first 6 questions on page 3. They're the simpler ones. But I'm going to carry on now with page 2, the Kahn-Ingold pre-log priority rules. So, first of all, let's find out if it does have geometric isomers. Well, that carbon's got 2 different things on it, and that carbon's got 2 different things on it. So, yes, it's going to have geometric isomers. Now, rule 1 says that I need to give the highest atomic number priority. So, for this carbon here, my highest priority carbon group, my highest priority group is this one because carbon has a higher atomic number than hydrogen, just like the other ones we met. So that is the highest priority group on this side. Then over here, I've got carbon, I've got carbon again. So I'm not going to be able to distinguish it just between those two. I'm going to have to look at number 3, rule number 3 for this one. Rule number 2 and 3, I look for the next atom. So this atom's bonded to 3 hydrogens, whereas that atom's bonded to 2 hydrogens and an oxygen. Okay? So the oxygen is actually a higher priority than those hydrogens. So, I've worked out which my highest priority groups were. So I've got those 2, it's useful to circle them. Put my ruler across the middle this time. Now, are they both on the same side? The same side, or are they on different sides? They're on different, so that must be an E isomer. Okay? I'm not going to bother trying to name that one, but that is how we use those rules to decide on which isomer it is. Okay, so we could, of course, with these ones, we could have done that exact process. We could have circled the highest priority, then stuck our line in. Okay? Thanks for watching.